All right, gang. Sorry for the abrupt ending in the previous video, but I got distracted um, and it didn't go well. So I deleted a little bit of that. What I want to do, I want to illustrate the prediction interval, but I want to use a different data set. Namely, I want to use the body fat. So I'm going to predict body fat from thigh. And the goal is to create a 90%. Y'all have to remind me because I'll be on tunnel vision here with 95% cruise control, if you will. But let's do a 90% prediction interval for the mean body fat when our thigh measure is 54.3. Notice the 54.3 is actually a measurement from the data set. So those are the type of prediction intervals that we are focusing on. Focusing again on predicting the mean from a data point that was used to create the model. It's very, very subtle difference, but and once I finish this illustration, we'll get into the other part. So essentially what I need is I need the predicted body fat for thigh, so I obviously need to create B1 and B2. So I'm going to go ahead and B1 and B2. Where did that come from? B0 and B1. So I'm going to go ahead and just create my model. I'm going to create these things a little easier. Um, so our coefficients would be negative 23.63 and the slope is 0.8565. So I can come up with the fitted for the model and focus on um, the fourth case. So the fitted for the fourth case, let's just call that 22.88. So in my confidence interval, I know that this is going to be 22.88. And of course, the tough part is going to be finding the variance. The T critical, again, we have sample size 20, so I'm going to use QT. But I'm focusing on a 90% confidence interval, so I have 10% missing, which means 5% goes in the left tail. So instead of using a 0.025, I use 0.05. And I got a smaller sample size here, 20 minus 2, obviously 18. So the T critical for this calculation is 1.734. So now I have to just pound my way through the calculation of the variance. Now, for the mean square error, kind of cool actually, because the mean square error is just the sum of the errors squared, which is just the sum of the errors. What am I doing here? Of the residuals squared divided by the degrees of freedom, which would be equal to 18. So mean square error here is going to be 6.30. So check. Next thing I need is 1 over n, so 1 over 20. And then I need, now I think I made an error in the last video. I think I just put an x there instead of the x of h. This needs to be the value at which we're actually making the prediction. So minus the mean for the x's. So again, I'm just going to take care of the numerator here. And I'm doing this for a reason, because I want these stored, because here in just a second I'm going to do a different type of interval. And it's going to use a lot of this stuff, so I want to be able to recall it very quickly. So the numerator for that part is just going to be the value for x sub h, which is 54.3, minus the mean of the thigh, and I need that quantity squared. Now the denominator is just going to be the sum of the deviations for x squared, so we'll do I'm going to do it all in one setting here. So I want the sum of the all of the x sub i's, which are the thigh, minus the mean of the thigh, quantity squared. So I can do the variance as the mean square error, 1 over 20, plus the numerator divided by the denominator. Oh, this I have to put times there. And then, of course, the standard deviation, square root of the variance. So the standard deviation here is going to be 5.603. So the 22.88 minus 1.734 times 0.5603. So the predicted interval will be 21.91 to 23.85. So what did we just find there? For a constant thigh measure of 54.3, the predicted mean body fat with 0.90 confidence is somewhere between these two values. Now, I want to change to a different type of interval. Again, that interval is predicting the mean from an observation that is related to or was used for the model. I want to switch now and do a prediction interval for a new observation. So what's the difference? In this example, suppose that we've created our model, which we have, but we have someone new walk in, 2 or 3 months down the road that's not associated with the 20 people, or not part of this data set of the 20 people that was used to create the model, or in some way closely related to that. So again, this is a prediction of a new interval. So our focus here is on the predicted value for y sub h, but again, it's a new value. Everything is the same as before, so I'm not going to beat a dead horse here and go over all that again. But the difference is the variance for the predicted changes a little bit. It just gets one additional term. So it may be pretty clear why I wanted to okay. Maybe clear why I wanted to save some of this stuff up here, like denominators and numerators, because you see everything, a whole lot of it is repeated, the same. The only thing different is there's more variation for obvious reasons. Now let me pump the brakes a little bit there. is it obvious why the variance would be higher for this type of problem than it would for a mean? Well, I think when you pull one person out, before I was focusing on one value, right? But now I'm looking at a new observation, again, focusing on one subject. Well, when one subject comes to me, I really don't know what they're going to do. It's kind of like my golf game. You know, I go out, last year, I'm getting on a tangent here. Last year, the best round I shot was a 68. The highest round I shot, I think, was maybe an 82 or something. There's a lot of variation there, right? So when I go out on a particular day, I don't know what I'm going to shoot. It's really, I'm that crazy. Can do anything. But if I look at the average score for next year, I can get a pretty good indication of what it's going to be. Because, again, collectively the scores go together, and it's easier to predict a collective measurement than it is a single measurement with a lot of variability. So, again, process is the same. We still have the y that's predicted. Plus or minus the t critical. And we have at times the standard deviation for the predicted. All right, so let's just create some new measure. So let's say that the thigh measure is, I don't know, it has to be something in the domain. So let's just say it's 50. But it's a new observation. So we're not predicting a mean, we are predicting a body fat for this particular person who has a thigh measure equal to 50. So, really it's, we take negative 23.6345 plus 0.8565 times the 50. So we get a predicted body fat of 19.19. Next thing I said, we're going to do a 95% confidence interval, so I'll do QT, but 0.025 this time. Degrees of freedom 18. I'll tell you what, I don't want to do that. I want to keep the 90% because I want to illustrate how much larger, wider the confidence level is. So I forget, what was it, 0.196 or something. Yeah, so 1.734. And then I need to find the standard deviation. So what I can do is I can go back up to this, the variance. The only thing I need to do is just add in the 1 plus. That's the only difference. I'm going to rename it as variance new. Standard deviation new is 2.572. Now, before the standard deviation was 0.56, we have a lot more variance again, and this is one thing that's in practice, frustrating with these types of confidence intervals is the variation within the interval is usually so wide that you really don't get that great of a prediction. But anyway, we can certainly. I never trust R on order of operations, so I'm a little bit. All right, so the prediction interval somewhere between 14.73 and 23.65. Now compare that to the interval before. Uh, the interval before we went from what 21.9? No, that's not right. Yeah, 21.9 to 23.8. So only about a variation of 2 units. Where here we've got a variation of about 9 units. But again, the difference is because we're predicting for one particular person and not a mean for a group of collective observations at a particular x sub h value. Well, the next video, I dive into R and show you how there's some built-in features, functions in R that where you can make these calculations. And I try to nail down even more the difference between calculating a mean and calculating prediction of a new observation. So, all right, gang, take care.